Today, we're going to pull back the curtain on one of the unsung heroes of our digital world, the adaptive filter. Now, you've probably never heard of them, but I guarantee you use this technology every single day. They're the reason your phone calls are crystal clear and your internet is lightning fast. They're these incredible little pieces of tech that literally learn and adjust on the fly.
All right, so here's how we're going to break this down. First, we'll look at the problem these things are built to solve. Then, we'll get into what they are and the secret sauce behind how they learn. After that, we'll check out where they're working in the real world. And finally, we'll talk about the fine art of tuning them just right.
So let's start at the beginning, with a problem that plagues basically any kind of communication you can think of, signal distortion. Picture this. You send a perfect, clean, digital signal out into the world, whether it's through a physical wire or just through the air. But the journey, it's rarely a smooth one. And that pristine signal almost never arrives looking the way it started.
So what's causing all this mess? Well, a huge culprit is something called intersymbol interference. See, when a pulse of data travels through a channel, it tends to get, well, smeared out. Its energy spills over and starts to bleed into the pulses right next to it, making everything a jumbled mess.
And you can really see the problem right here. That super sharp, distinct pulse on the left, it turns into that messy, muddled wave on the right. You completely lose the clarity you need to tell one piece of information from the next. And here's the real kicker. This distortion isn't a constant. It's always changing, which means a simple, one-size-fits-all filter just can't keep up. So if the problem is a moving target, what do? Well, you need a solution that can move with it. You need something that can adapt in real time.
And that right there is the adaptive filter. This isn't your standard static filter, it's a smart filter. It has this amazing ability to tweak its own internal settings, its coefficients, as it works. It's basically got a built-in feedback loop, so it can learn from its own mistakes and get better and better over time.
The best way to think about it is like the autofocus on a camera. As the subject moves, the lens is constantly making tiny adjustments to keep the image perfectly sharp. That's exactly what the adaptive filter is doing, observing, comparing, and correcting, all to get the best possible result.
Okay, but how does it actually know how to change? Let's pop the hood and look at the brain of the operation. It's an algorithm that's surprisingly simple but incredibly powerful, called the least mean squares algorithm, or just LMS for short. Now, before a filter can learn, it needs a way to grade itself. It needs a report card. And it gets one by calculating something called the mean square error. I know, it's a bit of a mouthful, but the idea is actually super simple. It's just the filter asking itself, okay, on average, how wrong am I right now? And the algorithm's entire mission, its only goal in life, is to make that error as small as humanly or digitally possible. You can kind of imagine the error as a giant valley. The algorithm's job is to take one step at a time, always heading downhill, to find that single lowest point at the very bottom.
And the way it finds that low point is through this really elegant three-step loop. Step 1, it produces an output. Step 2, it calculates the error to see how far off it was. And step 3, it uses that error to make a tiny little correction. And then it just does that again and again and again, getting a little bit smarter with every single loop.
And this right here, this is basically the entire instruction manual in one single line. The filter's new settings are just its old settings plus a tiny nudge in the right direction. And that nudge is based on 3 simple things: how big the error was, what the input was, and this thing called a step size, which tells it how big of a step to take. All right, so enough theory. This learning loop is obviously incredibly powerful. So let's talk about the cool stuff. Where is this magic actually happening in our day-to-day lives?
Seriously, this stuff is everywhere. Channel equalization is what makes high-speed internet possible in the first place. Those amazing noise-canceling headphones you love? Yep, that's an adaptive filter listening to the noise around you and creating an anti-noise signal to cancel it out. It's also the secret to compressing speech files, and thank goodness, it's what kills that awful echo on a conference call.
But you know, it's not quite as simple as just flipping a switch. Making a filter learn effectively is a bit of an art form. It's all about finding the perfect balance in how it learns.
Remember that step size we saw in the formula a minute ago? Well, that's the master tuning knob. It controls how aggressive the filter is. Does it take big, giant leaps toward the solution, or does it take tiny, careful, little steps? And this is where you get into a classic engineering trade-off. If you pick a large step size, the filter learns super fast. But it can be really unstable, kind of like a race car that's hard to control. it might overshoot the best solution and actually create more noise. But if you pick a small step size, it's slow and steady. It's way more precise and will get to a much better answer eventually. So there's no single magic number here. Engineers have to carefully pick a step size that strikes just the right balance between speed and accuracy, and it all depends on the specific job the filter needs to do.
And that's really the profound idea here, the big takeaway. The LMS algorithm shows us that with a very simple set of rules, measure how wrong you are, make a small correction, you can create systems that show incredibly intelligent, adaptive behavior.
It's a foundational concept that goes way beyond just cleaning up signals. It really makes you wonder, as our systems get more and more complex, and the amount of data they have to learn from grows exponentially, what amazing things are they going to learn to do for us next?